Thank you, Ken, and thank you everyone for joining, for logging in to watch my talk on detecting deepfakes. It's a pleasure being here, and I want to start by thanking IMVC organizers for bringing me over. It's unfortunately I couldn't come in the last few years, and so it's a great pleasure being here again. I'm only sorry that I can't be there in person. So because this is a talk on deepfake detection, I guess none of you is going to be surprised if I say that this video is a fake. This is actually the original. If you look at this closely, you may be able to see some discolorations, some lighting problems, but I hope you agree with me that if I had shared this video online someplace and it popped up on your screen, then you wouldn't necessarily have known that this is, or suspected that this is a manipulated face, that this is a fake. Deepfake methods have been around since 2000 and, to my knowledge, at least 4, but over the last 3 years or so, since 2017, they're becoming better at faking photorealism. This is not really surprising because the recent GAN-based methods are explicitly trained to fool other networks and humans in the photorealistic in their photorealistic output. So thinking to fool us and other machines and thinking that these are real videos, these are genuine. Making things even easier are methods that have been released over the last year. I think the first one was our FSGAN from 2019. These are methods that not only try and make results even more realistic, but they alleviate much of the, or remove many of the hurdles in creating deepfakes. So the original deepfakes required a lot of subject-specific training data and then required hardware and GPUs in order to train on that subject before you can swap that subject onto new media. And FSGAN and the methods that came afterwards removed that need, and you can now apply deepfakes to people's faces without having to train on them. If it's not already true today, it will very soon be true that people without any expertise and without any specialized hardware could generate such deepfakes and share them. Now, it's important to note that the methods that were originally proposed, face swapping methods, long before deepfakes, were originally proposed with good intentions in mind. People were talking about them in the context of privacy preserving, replacing people's faces on their public profile pages. People were talking about them in the context of virtual try-on. People were talking about them in the context of even face reenactment, making dubbing and voiceovers look more realistic, moving people's lips in a way that matches the voiceover. So there's a lot of good use cases for this. But just like any technology that mankind has come up with since pretty much the wheel, this technology can, and as most of us probably know, is being misused, which raises the natural question of how do we know that what we're watching or what we're looking at on the web, on the news, is genuine and not actually a misuse of this technology, which raises the problem of detecting deepfakes. Maybe the vanilla approach to detecting deepfakes, and one that is still working quite well today, is to look for method-specific artifacts. Different generators leave behind telltale signs that this is not a genuine photo. Here I collected a bunch of examples from a public benchmark for deepfake detection, where we as humans can actually spot the artifacts. These are actually failed swaps. But you can train methods to seek these visible artifacts, but also imperceptible artifacts that reflect in minute changes in pixel values. And then once you see a lot of examples like this, new media comes in, you apply your classifier and it tells you, yes, I'm seeing these artifacts that I've seen before. I know this is a fake. Now, this works quite well in general, but this approach has its limitations. And a particular limitation is around the fact that different GANs and different generators have different output distributions. One way of qualitatively illustrating this is with this figure over here. Different faces here were generated by StyleGAN, ProtoGAN, and face-to-face, and the color of the margins reflects the method that was actually used to generate each example. We extracted some high-level embedding, projected it to 2D, and this is the figure that you're seeing right now. Again, this is a qualitative experiment, and you can use different features for this, but ultimately what you'll see is what you're seeing here, where different colors, or different methods that is, tend to clump together. So if you're training something on a specific method, it won't necessarily be able to say anything about images that were generated by other methods. And of course, even in this example, you have all this space around these images, which was populated by what? It was populated by genuine photos, or populated by photos that were created by methods, but by other existing methods, or maybe will be populated by methods that are yet to come. Broadly speaking, the textures that are trained on one or a closed set of generators do not generalize well to others. And so this works, but this has its limitations. And this raises the interesting technical problem or technical challenge of how do you develop something that is generic, that can detect fakes that were generated by unseen methods. Making this, of course, more challenging is the fact that these methods, as I mentioned earlier, are trained to become more and more and more photorealistic. So to detecting these fakes, it's becoming harder and harder. Now, before talking about particular method of detection, I want to use this opportunity to present the Deepfake Detection Challenge, or DFDC. DFDC is not the only benchmark or challenge out there for detecting deep fakes, but it has some very unique properties that I think would be interesting to people listening to this talk, even beyond their interest in deep fake detection. The Deepfake Detection Challenge was created by a consortium of both academic and industrial partners, namely Facebook, AWS, and Microsoft, as well as the Partnership on AI. And for those who don't know, the Partnership on AI is itself a very large consortium which focuses on responsible use of AI. And this challenge was released in order to leverage the abilities of experts and non-experts in trying to solve this very challenging problem. The Deepfake Detection Challenge includes videos such as this. She'll wake up in a second and start moving around. Here you go. So this is a movie. It includes videos such as this. It has some features that, as I mentioned, are extraordinary. One of them is the fact that this data set includes 3,500 individuals. Not a great number if you consider some of the benchmarks out there that the scientific community is regularly using. But what's special about this is that all the participants signed consent forms acknowledging that their videos and faces will be used for face manipulation and detecting face manipulations. And this is a good place to stop and say that for decades now, the scientific community, we as a scientific community, have been using data sets that were mostly scrubbed from online sources, which means the faces appearing in them did not provide consent, which raises serious privacy concerns on their use case. Another thing that this benchmark does is it tries to balance for diversity, so men, male, female, different age groups, and skin tones. Also something that is not standard in many of the academic benchmarks out there. The data set itself is huge. It contains around 40 days of raw video footage filmed in a variety of real-world settings, not just this boring plain background. There's also multi-people and cluttered backgrounds. And it's released under open source license. The asterisk here is to remind you all that I am not a legal counsel, and you should seek your own counsel before using this data set for anything. But the intention is to make it usable for a variety of use cases. The data set contains examples of, aside from the raw footage, it contains examples of faces manipulated by a variety of techniques. Some of them leave behind very visible artifacts, some of them don't. Importantly, however, some of the methods were held out. So we produced some examples and by methods that were not released as part of the public data set. This dataset was released about a year ago as a Kaggle competition with $1 million worth of total prizes. Unsurprisingly, this drew a lot of interest with over 2,200 competitors and close to 35,000 submissions. Now, if you're bedazzled by the $1 million bold sign, I'm afraid to say that the competition is now actually closed. But I will tease that we're looking into a next generation DFDC with some very cool surprises and unique new features. So please stay tuned. Now, with this number of submissions, this allowed us to dive in, reach a lot of conclusions, and see a lot of numbers. I've sifted through that, and I just want to bring you one result, or one important result from this this challenge, which is captured by this scatter plot here. In the scatter plot, each point is a method. Its position along the x-axis is its score on the public benchmark. Its position along the y-axis is its score on its accuracy, the deepfake detection accuracy on the private held out set, which I remind you includes methods that were not released to the public set. And I want, and this scatter plot is interesting because of a particular point which I want to draw your attention to, was this point right here. This point here is important because, as you can see, it's the highest scoring point on the public set. But it's way, way far from being the best performing method on the public set, on the held out set. In fact, it's somewhere in the middle of the pack. And that's a quantitative signal, quantitative evidence that generalizing beyond known methods is a hard problem. Okay, so how do you solve this problem? This has been the focus of a lot of research in the past 1 or 2 years. I think some of you may have heard this method that came out recently, which tries to look at micro gestures and pulse and things like that. I want to talk about the method that we just released to archive about a month ago, which beyond providing very nice results, also reflects some observations which go beyond deepfake and say something about the perception of identity in photos. So I think I hope you enjoy them. Observation number one. All face swapping methods, and I should maybe point out that I'm talking about face swapping in particular right now. I'm not talking about new view synthesis, not talking about face reenactment where you're just changing a person's expressions. I'm talking about swapping one face over another. All face swapping methods in the past and probably also in the future have one thing in common, and that is they manipulate just the region of the face and not the context, not the rest of the photo. And I'll visualize that for you. Here are 6 different face swapping techniques from recent literature, and we've painted in purple or blue the region that actually manipulated by these methods. As you can see, deepfake, for example, manipulates just a fixed bounding box in the center of a fixed box. I'm sorry, in the center of the face bounding box. Face-to-face, neutral textures, and I think face swap all rely on some combination or some function of the convex hull of detected facial landmarks. And FSGAN does accurate segmentation and just manipulates a segmented region. Now, this is not a coincidence. All these methods apply just to the face, just manipulate the face, because trying to manipulate anything outside of the face is much, much, much harder. Hair, for example, is notoriously difficult to model and manipulate. So from a scientific and engineering standpoint, it makes a lot more sense just to focus on something that's easy and avoid doing something that's hard, like manipulating face regions, hair regions, context. This is true for other methods that exist today, and it's likely going to be true for methods that come out in the future. Hair in particular is still a hard problem and is likely going to be going forward. Okay, so this is observation number one, and it tells us that we have 2 regions in the image. One is the face region, and one is the region around it, which brings me to observation number 2, reflected in this ROC curve. And this ROC curve reports results of 4 different tests on the good old label faces in the wild benchmark. I should maybe note that, say that I'm not recommending anybody use label faces in the wild LFW these days. It's saturated. We're only using it here to prove a point. But as a benchmark, it's of course saturated. The first result, the blue line, is standard vanilla. Train a network on a big data set of faces and then apply it to determine if two faces are same and not same. And the results are near perfect, which is consistent with the quality of face recognition in 2020. The next result is almost the same. In this case, we segmented just the face regions of our entire training set, trained on these segmented regions, and then applied it to segmented regions in the test set. So we're just looking at the face without the context. The results are almost identical. It's like a very minor hit in performance. Not really surprising because the face includes a very strong signal for identity. That's why we call it face recognition. The next result is a little bit more surprising. The next result, what we did is we segmented both training and test set, and again, trained a new network on the segmented training set, but this time we were looking just at the contexts. So both training and testing did not include the face region, just the context. And what's surprising about this is that it's an almost perfect result. And what this says is that even without the face, just looking at the hair, the neck, maybe the ears, we're getting a very, very strong signal on a person's identity, strong enough so that face verification is near perfect. Finally, and what I think is the most interesting result, is this red line here. Now, this isn't a high score by today's standards. On LFW, as I mentioned earlier, you can get perfect results. I should say that we didn't really try to optimize this, but this is still a very high result if you consider that chance is 50%, and this is way above that. In this experiment here, what we did is as follows: to compare two faces, we start off by segmenting them just like we did last time. And we have two networks, one trained on the context and one trained on the face. Here, we take not the representation layer as representation for the face and the context. We take the output. And the outputs of these two networks are in identity space. So it's the same output space, which allows us to compare the output of the context network with the output of the face network and just look at the distance between them. And we're doing the same with the row switched, sum those up, and then threshold that in order to get the ROC curve that you're seeing earlier. What we're trying to ask here, and what we're interested in seeing is, okay, we know from the previous results that the face provides a strong signal for identity, and the context provides a strong signal for identity. But is it the same signal for identity? And the fact that this curve is this high means that in many cases, it most certainly is. Putting that into words, if it is same person, if the two photos are the same person, the face and the context will match. If these are different people, the face and the context will mismatch. So our intuition, if I should sum it in one sentence, is take a single photo. We're moving away from the face verification two photo use case to a single photo. We're just looking at the face and comparing it to the context. Take a single photo, look at the face, look at the context, and seek inconsistencies. If you find these inconsistencies, that's a telltale sign that something is wrong with this photo, that this may be a fake. To give you a qualitative example of this, consider these two images. On the left, at least to me, I thought this was, when I saw this the first time, I thought this was a genuine photo, but this was picked up by our method, and you can see why. The face is wearing eyewear, the context isn't. And eyewear is usually associated as, usually reflected as identity-specific feature in most benchmarks. On the right, it's a little bit more subtle, but the face region presents as a male gender, and the background or context presents as a female gender, and there you have another mismatch. These observations translate into the following system design. It looks a little bit complex, but I'll walk you through it. It really isn't that complicated. Start with pre-processing, taking video frames or a single photo, running face detection, and then our segmentation and cropping method, giving us a face bounding box, segmented face and segmented background. we have one part of the system, one data flow region or whatever, one part of the system that is sort of your standard, let's look for known artifacts approach, the one that I started, that I described a few slides before. Yes, it doesn't generalize, but a lot of times people are lazy, they use the same method again and again, which means that if we can take advantage of these artifacts, why not? The interesting part of this system is here. In this part, we're taking the foreground of face region, feeding it through a network that was trained on faces, and then looking for its output, and doing the same for the background and looking for its output. These outputs are then normalized, subtracted, concatenated with a method-specific representation, and then fed into a discriminator trained to say fake or not fake. In the interest of time, I won't walk you through all the different results on the different benchmarks that we've trained on, but this was shown to generalize very well, and I hope you trust me that it's all good. We're state of the art, at least when we release these results. And with that, I think I'm at time, so I'll just leave you with some closing thoughts. Face manipulation methods, face swapping, face reenactment have been here long ago, longer maybe than a lot of people realize. Again, 2004 or even 2002. And they will likely become more and more prevalent as results become more photorealistic and the technology becomes more and more accessible. This leads to, and I should say, and this is just faces, there's other domains where there's both opportunities and risks in doing these manipulations. It's not the faces as a domain, that's certainly not where these things are stopping. Next is, this leads to interesting, challenging scientific problems of seeking signals for generator agnostic detection, for detection that is not dependent on a particular generator function or particular generator model. Of course, this becomes harder and harder as these generators become more and more photorealistic and better at mimicking real, genuine images and videos. And finally, moving outside of the context of science and technology, there's also education and legislation problems involved here. Very similar to automobiles, we need to be trained to drive safely, and we need legislation to make sure that cars are safe. This is a new technology that, as I mentioned earlier, has risks, and those risks should be mitigated by us, but also by educators and legislators. And with this, I thank you all for listening to me, and I'll leave you with a short bibliography of the papers that I mentioned in this talk. Thank you very much. I think you're muted, I didn't hear.
Yeah, so thank you, Tal. It's really fantastic, and although you are far away, I think that I will express the feelings of the entire community when I say that we feel that you are here with us and we really miss you. So here are some questions to challenge you. The first one is from Avram Goldberg. Why, and this was also bothering me, why is accuracy higher on private sets? What's so special about private sets that accuracy is better there?
Accuracy is better. So the two sets, so the accuracy is not better on the private sets in general. Some methods, as you've seen, actually had much lower accuracy. They dropped in accuracy. These are two different sets, so there's no expectation that the accuracies will remain the same. And it could be that it also has a lot of simpler examples. It's, I think, much smaller set. But I don't know that there's a trend of numbers being easier on that particular private set or private sets in general. I don't know that that is actually the case.
I see. Okay. Another question from Itai Krischer. Did you try this on dark-skinned faces, and do you see any difference when you look at different people with different colors? You know, all the discussion of bias in AI is very, very hot, and so how invariant it is to gender, to color, etc.
I'll start by saying that as an org and as a large part of my personal interests, and I don't want to speak for anybody else, but the large part of my interests are aligned with the idea of fairness and mitigating bias. DFDC in particular was designed to be balanced across different skin tones. We didn't run bias analysis on these results. Not that I'm aware of. I don't remember doing that, but the data set itself and the numbers it reflects performance on both on different skin tones, as well as different genders and different ethnicities. This is the DFDC. The Face Forensics ++ experiments, I don't know that that's true for them. I'm not saying it's not, I just don't know.
Okay, I see. And one last question. I remember, especially when I visited the GTC conferences, where, you know, there was a lot of discussion on the uncanny valley, and that at some point, you know, things are just not working anymore. So do you think with this deep AI and guns, etc., do you think that we actually were able to jump over the uncanny valley?
Absolutely. Absolutely, in a big way. And look, I don't want to give a blanket statement. I mean, you've seen some of the results that I showed from DFDC. You can see artifacts in some of them. But in many cases, it is very, very difficult to tell that something is that something was swapped or generated by a machine. In this talk, I was talking just about face swapping. There's also just face generation from scratch, StyleGAN type or StyleGAN 2 type things. And if you look at the results that they produce, I don't know, maybe it's my old eyes, but I can't tell that these are fake people that were synthesized by a machine and not real photographs of people. So I think that, yeah, absolutely.
Yeah.